Good evening, everyone. Welcome to Week 10 live interactive session of Operating System Fundamentals. We'll just take a quick recap of what was discussed in the previous week and then look into a couple of example problems. So last week, the session was on paging, then about TLB, then multi-level paging and demand paging. So we'll get started with TLB. Basically, with paging, one of the most difficult part with respect to paging was that the number of memory access that was required. So, we have the page table and then we have the frame. So, this is the physical memory. This is the frame, and this is the page table. So page table is also actually loaded in the memory itself. So when a location need to be addressed, first this page table need to be looked up, and then we get the frame number information, and then the respective frame will be accessed. So this requires a memory access, and this requires a memory access. So this is this time is much higher. To memory access. So to reduce this time, there is something called TLB, that is translation look aside buffer, which is a very fast memory. So this TLB will hold the page and frame number information. Okay, so it will be it's not a cache, kind of a cache. So it will have something called the page number and its corresponding frame number. So when a process is executing, so from the CPU address will go to both the TLB and also the page table. And if an entry is found in the TLB, that particular frame will be taken and then processing will continue. Otherwise, uh, the information will be retrieved from the page table and then again the execution continues. So since the page TLBs are smaller in size, the probability of we cannot hold the whole every process paging related information in the TLB. So sometimes when we are trying to access a page, the entry may be there, may not be there. So if the page table entry is not there, if it is there, then we say it is a hit, and if it is not there, we call it as a miss. Okay. So in case of hit, we will get the entry, the page and the frame number information from the TLB. But in case of a miss, it will be retrieved from the page table. So now let's one simple one example question that was given that virtual address of 64 bits and physical address space of 48 bits. Page size is given to be 8 KB. And it is told that this is word addressable. So by default, when nothing is mentioned, we take it as a byte addressable. That is, for every byte, we need to have an address. When we say word addressable, an address is required for a word, and the size of the word also normally will be given in question. So in this question, each word is 4 byte. So a 4 byte, this will be 1, 2, this is a word, and this 4 bytes will be addressed. Then and the other word 2. This is word 1. Word 2 will be addressed. This is address 1. This is address 2. It's a difference between word addressable. Whereas byte addressable, so this is like totally 8 bytes, right? So this will be address 1. This will be address 2, like that. This will be address 8. So this is when it is byte addressable. This is how when it is word addressable. So, so it is told that the TLB can have 128 valid entries. So using this 128 valid entries, how many virtual addresses can be translated? Okay, so let's see here. The page size is 2 power 13, but it is word addressable, right? So the page size will be 2 power 13 by 4 byte, which is 2 power 11. Okay, because we don't, this was when it was byte addressable, but since this is word addressable, we need only 2 power 11 different addresses to address all the words in that page. Okay, so this is the page size. So each page will have 2 power 11 different words. Okay. So that is about the page size. Now, in TLP, what we store is we store page information, right? As I saw in TLB, this is what we store. Each entry will have, this will have the page number, this will have the frame number. So this total is 128. We can have 128 different entries. So each page number, this will go to a frame, which will address to power 11 different locations, right? So with 128 different entries, we can have 128 different page numbers. So with 128 entries, 128 different page numbers. And within each page, we can have 2 power 11 different addresses. So the distinct virtual addresses that can be translated using a TLB will thus be 128 into 2 power 11. Which is 128 is 2 power 7 into 2 power 11, which is 2 power 80 different addresses. Okay. So this was one question. Then the other topic discussed is about the hit and miss of page and the amount of time it takes to access the TLB. Okay, so let's take a look at that TLB access time. Yeah. So how much time, effective access time needed to retrieve a location or access a location. Okay. So there is, so we have, so to access a physical memory, to access a physical memory, if when we have a TLB, we first access TLB, then access physical memory. Okay, so this access TLB can be a hit or a miss. Access TLB can be a hit or a miss. If it is a hit, then we go to physical memory access. But if it is a miss, then we will be in parallel, we will be accessing the page table access followed by memory, physical memory. So the time that we take here to access is first is the time to access the TLB in P1, then the time to access physical memory, that is T4. In case of hit, okay. So in case of hit, it will be T1 plus T2. Whereas in case of miss, the time will be, we will again, because we will be accessing the TLB first, it will be T1 plus we will be accessing the page table T2 plus then we will be accessing the physical memory. So since both these are memory access, we are marking these as T2 and T2. So this is the time required to access a effective memory access time in case of hit and miss. So in general, we will have some misses and some hits. So we call the number of hits that we get as hit ratio and the number of misses as miss ratio. So in general, the hit ratio will be provided and miss ratio will be 1 minus hit ratio. One minus hit ratio. So for that, the example that was discussed in the class. So there the hit ratio was given as ratio is given as 80%. Let's see this example. Hit ratio is given as 80%. Memory, sorry, TLB T1, TLB access time. Access time is equal to 20 nanosecond and memory access time equal to 100 nanosecond. So the effective memory access time is equal to hit ratio into T1 plus T2 plus miss ratio into T1 plus T2 plus T2. So here 0.8 into T1 is 20 plus 100 plus miss ratio is 0.2 into 20 plus 100 plus 100. 0.8 into 120, which is 240. So this is how we can complete the effective memory access time. Now let's see a couple of examples on the memory access time. Give me a minute. There is another question in the previous year's question paper, so we'll take that also. Here, the question is in a paging hardware with a TLB page table and all pages are in physical memory. It takes 10 milliseconds to search TLB, 10 millisecond, and physical memory access takes 80 millisecond. Physical memory. If the hit ratio is 0.6 and what is the effective memory access time? The question is effective memory access time. So the formula is hit ratio into TLB hit time plus miss ratio into miss time. So here the hit ratio is 0.6 into TLB hit time will be TLB access time, that is 10 millisecond plus 80 millisecond. Then miss ratio is 1 minus miss ratio equal to 1 minus hit ratio, which is equal to 1 minus 0.6, which is 0.4. So it is 0.4 into 10 plus 80 plus 80. So effective access time, which is equal to 0.6 into 90 plus 0.4 into 170, which is 54 plus 122 millisecond. Okay, so this is one question. Another question is so we have a TLB search time given as TLB search time 20 nanosecond. Memory access time is given as 100 nanoseconds. Now TLB hit ratio is given as 80%, 0.8. So expected memory, what was the expected memory access time? So this is the question. So same like above, the formula is hit ratio into memory access time when it is a hit. So it is basically a TLB access time plus memory access time plus miss ratio into, when it is a miss, we access the TLB access time plus 2 into memory access time. This is 2 because first we access the memory for the page table, then we do the actual memory access. Here this is the actual memory access. Here one is page table access and the other is the actual memory access. So if we substitute the values, expected memory access time will be hit ratio is 0.8 and miss ratio is 1 minus hit ratio. 8.8 into 20 plus 100 plus miss ratio is 1 minus hit ratio, that is 0.2 into TLB access time was 20 plus 2 into 100. So which is 0.8 into 120 plus 0.2 into 200 plus 20, 220, which is 0, which is 16, 96 plus is equal to 140 nanoseconds. Okay, so this is one. We will see a couple of things in case if you have any doubts, let me know. Another question. There is a two-level paging scheme with TLB. And the TLB access time is given to be 20 nanoseconds. Physical memory access time is given as 100 nanoseconds. And TLB hit ratio 0.8. So when we have multi-level paging, the number of I think multi-level paging was already discussed. So in the last week. So how multi-level paging? What happens is, so we'll have one level of paging followed by another level of page table access. This is level 1. This is level 2. We can have a level N. And then we go to the actual frame. Then here we access the actual memory content. So these are all memory accesses only, but here we are accessing the page tables from the memory, and this is the final data content access. Okay, so this one, so in case of a TLB miss, so in case of a TLB hit, it will be same as TLB hit. So there will be a, so CPU address will go to both here and TLB. Okay, so in case of TLB hit, it will directly go here. But in case of TLB miss, it will go here, here, here based on the number of levels. Okay. So if I have, if suppose we had a 3-level paging. So in case of TLB miss, so first there will be a TLB access time. TLB access time will be there. Plus we will have L1 page table needs to be accessed. This is nothing but memory access. Then L2 page table need to be accessed, which is again a memory access time. Then if this L3 has to be addressed, and then we will have the actual memory access. So if we have N level paging, so if I take 3 levels of multi-level paging, this is 1, 2, 3. Then the actual memory access. So for 4. So we have 4 memory access in case of 3-level paging. If I had only 2 levels of paging, if it was only 2 levels, that is level 1, level 2, and then the physical memory, that is frame. Then I have this accounts for one memory access time, this accounts for another memory access time, and this will account for another memory access time. So if I'm having 2-level paging, in case of a TLB miss, there will be 3 memory access. So if we have, we will have L1 access time plus L2 access time plus frame. This is nothing but all these 3 are memory access time. Okay. So if we have N level paging, then we will have N plus 1 memory access. So in this question, it is a 2-level paging. Okay. So in case of a TLB hit, so the formula will be effective access time will be, in case of a hit, hit ratio 0.8 into TLB access time, which is 20 nanosecond, plus the frame access time, which is memory access time, okay, 100 nanosecond. Plus, in case of miss, we have this additional accesses. We will have the TLB access, then we have this access plus this access. So we have 3 memory accesses, 3 into 100. So since it is a 2-level paging, we have 2 plus 1 memory access. So the answer is 0.8 into 120 plus 0.2 into 300 plus 20, 320, which is 0, 8 to 16, 96 plus 464. Which is equal to 160 nanoseconds. Okay. So this is how when we have multi-level paging with TLB, this is how we compute the access time. Let's say, and one more example. Now we have a 3-level paging with TLB. TLB access time is given as 20 nanoseconds. And memory access time is given as 100 nanoseconds. And the hit ratio is given as 80%. 0.8. So miss ratio will be equal to 1 minus 0.8, which is 0.2. So now we have 3-level paging. So in case of a miss, so for miss, we will have 3 plus 1 memory access. So effective access time will be hit ratio into TLB access time plus memory access time plus miss ratio into TLB access time plus 3 plus 1, 4 into memory access time, which is equal to 0.8 into 120 plus 0.2 into 420. Which is equal to 120 nanoseconds. So as you can see, as the number of levels in paging increases, the effective access time increase based on the hit ratios. Okay. Now another one more question. Here we are having consider a single level paging. TLB access time is given as 20 nanosecond. Physical memory access time is given as 100 nanoseconds. Now they have also given EAT, that is expected access time, 130 nanosecond. Now we have to compute the TLB hit ratio. What is the TLB hit ratio? So what is the effective? So putting it in the formula, 130 equal to, so let's assume that net hit ratio be equal to X. Okay. So 130 equal to X into 20 plus 100 plus this ratio will be 1 minus X into 20 plus 2 into 100, which is equal to 120X plus 1 minus X into 220. 120X plus 220 minus 220X, which is equal to 220 minus 130 equal to 220 minus 120, which is 100x. So 90 equal to 100x, which implies x equal to 90 by 100, which is equal to 0.9 or 90%. So the hit ratio is 90%. So this is how with this we can ask multiple, we can find out multiple parameters. So in another question, let's say another question wherein PLB access time we can find out. So for example, memory access time is given as 100 nanoseconds. Sorry, 100 nanos. PLB hit ratio is given as 60%. Expected memory access time is given as 160 nanosecond. Now, what is the TLB access time? So let us assume that let X be TLB access time. So now if we put it in the formula, it will be 160 equal to 0.6 into X plus 100 plus 0.4 into X plus 200. Single page, single level page. So 0.6x plus 60 plus 0.4x plus 80. So 1.0x plus 140, which implies x is equal to 160 minus 140, which is equal to 20 nanoseconds. Okay, so the TLB access time is found to be 20 nanoseconds. And one more similar question from this section. Another question is, this is again a single level paging. TLB. So TLB access time is when given as 20 nanosecond. Memory access time is what we need to find and given. Hit ratio is given as 50%. And expected memory access time is given as 170. So miss ratio will be again 1 minus 50, which is 50%. So substituting in the formula, we get 1. So we'll assume that let memory access time equal to x. So 160 equal to 0.5 into 20 plus x plus 0.5 into 20 plus 2x, which is equal to 10 plus 0.5x plus 10 plus x, which is equal to 20 plus 1.5x. So 150, 1.5x equal to 170 minus 20 is equal to 150. So x equal to 150 by 1.5, which is equal to 100 nanoseconds. This was couple of problems on memory access time given different parameters. How do we find the various other parameters? So that was on memory access time. And let's go to the other topic discussed in the last class. Yeah. So the with TLBs, yeah. So after TLB, the next topic discussed was on the hierarchical page tables. For example, till now we have seen that we have only seen page tables are there, and we assume that these page tables are in the memory, and then we refer it and get the physical memory location. But how large is this page table, and how are they stored in the physical? So page table also needs to be in the memory to be accessed, right? So how are they stored in the physical memory? Are they put in a continuous location, or are they also put into various pages and put into different frames? So the one of the major concern here when we have the with respect to this page table storage is the size of the page table. For example, if we consider a 32-bit logical address, and if you have a page of page size is equal to 1 KB, which means 2 power 10. Okay, so we have 22 bits for P, that is 2 power 22 pages, right? And if which implies that 2 power 22 pages means 2 power it is 4 MB. And if each entry is of like 4 bytes, then it will be like this is based for the entries alone. Now, if each page same table entry is of 4 bytes, then it will be like and if entry size is 4 byte, then page table size will be 2 power 22 different entries into 4 bytes, which is 2 power 4 into 2 power 20, which is 16 MB, which is like very huge. So if you see 16 MB is the total size of the page table, and our page size is only 1 KB. So to store, store So, how do we this is a very large memory, whereas the page size is only this much. So, how are we going to store this page table in memory? So, we have to put these page tables also in different pages only, that is on different frames. So, how are we going to scatter the 16 MB of page table? So, 16 MB is the page table size. So, number of pages needed to store the 16 MB will be page table size, that is 2 power 10. So 2 power 24 by 2 power 10, which is 2 power 14 pages will be needed. And where will these pages be located? How do we know, okay, to access this particular content, we need to go to this particular page location. It could be anywhere scattered across in the main memory. So there needs to be a proper organization so that one can access these pages properly and finally retrieve the data from the frame. So for this, we use certain hierarchical organization. One is hierarchical paging, the other is hashed page table, and the other one is in inverted page table. So in hierarchical paging, as I said here, this one large page table will comprise of multiple pages. So what we do is we will have something called an outer page. Then we will have so many inner pages. And then again, this multiple pages will be there, which would finally map to the frames in the memory. So the outer page will point to one of these intermediate page tables. These will point to one of these intermediate page table, and then finally we will get to the physical memory frame location. Before to get a clearer understanding, let's take a look at one example. Okay, so for example. So let's take a very simple small example. That is, let's assume that we have a total, we have 32 bytes of memory for the whole process. So 32 bytes of memory we have, and the page sizes. Let's take small example, and then we can move to larger ones. It becomes little more clearer. So the page size is 4 bytes, and page table entry equal to 1 byte. Okay, so to have, so the total memory process memory is 32 byte, and we have the page size as 4 bytes. So let us see how many pages will be needed for this process. So number of pages needed to store this 32 byte of process will be 32 size by size of the page, right? Which is equal to 8. So we will need 8 pages, okay? So now let's see, when we say 8 pages, it implies that we will have a page table with 8 entries. 1, 2. So this is what number of pages needed equal to 8 means. So we will have 8 entries in the page tables, 8 different entries. So each entry would represent one page. So this is the page table. Okay. Now what will be the size of this page table? The size of this page table will be how many we have? 8 entries, and each entry is of 1 byte, which is 8 bytes. Okay. So we need 8 bytes to store the page table. But we know our page size is only 4 bytes. So how many pages we will need to store the page table now? So to store the page table, we need 8 by 4, 2 pages. Right? So now this 2 pages, will have the, so this whole page table entry, that is 1, 2, 3, 4, 5, 6, 7, 8. This full entry will be stored in 2 different pages. Okay, into 2 different pages. So one frame, or one frame will comprise of this 4 entries. 1, 2, 3, 4. Sorry. 1, 2, 3, 4, and in the physical memory. And the other might be somewhere else. It could be here. So this is the first one, and this is the second one. 6, 7, 8. So these are the page table entries for this particular process. So it could be in this portion on the physical memory, and it could be in this portion in the physical memory. But how do the memory management unit know that where is this particular page present in the physical memory? Where is this particular page present in the physical memory? That is, so we need to provide that information also, since we have to. So to provide that information, we keep another page called the outer page, which will have, currently we have only two pages. So we will have a outer page table with two entries. One will tell that go here and the other will tell go here. So how it will be is that, so we have the, so how will be the logical address? Page size is 4 byte, which implies 2, and the other is 3, because we have total 5 bits, right? 32 bytes. So this 2 bytes will help us identify this 4 location, within the, sorry, this 2 will help us identify the, within the frame, the offset. And this 3, we further divide this into, this 3 is further divided into 1 and 2. And this 2 will help us identify these locations. And this 1 bit help us identify whether it is this one or this one. So this is the logic of multi-level paging. That is, when the page table size exceeds the page size, we need to split it into a number of different pages. We need to split it across to multiple pages. So now we need to gather this information somewhere. So where each page is being located. So we use certain bits of the virtual address space to identify where these pages are located. Okay, so in this particular example, we had a 5-bit address, 5-bit address, wherein 2 bits are used for offset within the page, and this 2-bit is used for accessing the inner page table. This 1 bit is used for accessing the outer page table. So this 1 bit, so if you take it, okay, so I numbered it from 1, 2, 3, 4. If we number it as 0, 1, 2, 3, 4, 5, 6, 7, then if you see here, this is like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. So if you see here, this 1 bit is 0 for all this 3, all this 4, and the other, the bit is 1 for all the. So it will help us using this bit. We can identify whether to go to this location or to go to this location. So this first bit, if it is 0, so sorry, the 0, 1. So if it is 0, you go here. Then you take this 2 bits. Then in this, you go any of these location. And then from here, you actually go to the actual data content. So if it is 1, go here. And then using the next inner page table bit, choose among this. And then you go to get the frame. So this is a simple multi-level paging example. Let's see one more example here. For example, now in place we use 32 byte and all. Now let's make it little bigger. So let's assume that the number of pages. Earlier we found out how many pages from the memory. Here they are telling that the number of pages. Number of pages is 2 power 15. Okay, and page size is 2 KB. Page table entry sizes 4 byte. Okay, so now let's first form the P and D. P and D. What is the displacement? Page size is 2 KB, which is 2 power 11. So displacement equal to 11 bits, and number of pages is so P equal to 15. Okay. So now let's find out what is the page table size. So we have these many pages. Okay. So this means that page table will contain that many entries. So that many entries into size of each entry. So page table size. So we will first see what is the page table size, then how large it is than the page size. So how many pages we need to accommodate the page table. We will see that, and then we will identify this inner and outer bits, how many bits we need for the inner page table, and how many bits we need for the outer page table. So here the page table size will be 2 power 15 into page table entry size, which is 4 bytes, that is 2 square, which is 2 power 17. So page table size is 128 KB. Okay, so this is the page table size. Now, number of entries in each page is so we have 2 power 11 as the page size, right? So in this 2 power 11 2 KB, 2 KB is the page size, okay? So in this 2 KB, this is nothing but how so in this page only we have to fit in our page table entries, right? This so we have the page size here. This is the page and this is the page table. So we have to fit this page table, a portion of the page table, to this page only. Okay. So we have to now see how many. So page tables are nothing but entries, right? Page table entries. So we need to see, we know each page table entry is a 4 byte, and we need to fix this page table to the page. So let's see how many entries can the page hold. Page is of 2 KB, that is 2 power 11, and each entry is 4 byte, which is 2 square, which implies 2 power 9 entries each page can hold. So each page can hold 2 power 9 entries. Okay. So now let us see how many pages we will need. How many pages we will need for storing the page table. So page table size is 128 KB. Page size is 2 KB. So number of pages needed. Page size, which is 128 to power 17 divided by 2 power 11, which is 2 power 17 minus 11. So this means that we need 64 different pages to hold the page table. Okay, so we need to, so we will have 64 different pages. Page 1, page 2, page 3, page 4, page, page 64, page 0, page 1, page 2, up to page 63 we will have to hold our BT. To hold our page table, we will have these many pages scattered across. So how do we identify 64 things are there? So to power, so we need 6 bits to identify these 64 different pages. And then within each page, we have 2 power 9 entries. Within each page, we have 2 power 9 entries. And we have 64 such entries. So in the hierarchical, this will be, we will have an outer page table, with 64 entries. So this will point here, this will point here, this will point here, like that. Will point here. Okay. So this will be the outer page table. This will be the inner page table. And then we will have the actual physical. So these are also on the physical memory only, but just the actual data. Okay. So this, as you see here, this will remain same. This 15 bits is split across 9. 6. This 6 bits will be used for the outer page table addressing, and the next 9 bits will be used for the inner page. So it is split to, so we have 11 offset, then we have P1 and P2. Sorry, P1 outward and P2. So this is 6 bits and this is 9 bits. This 15 bits is split to 6 and 9. Okay. So this is how the hierarchical paging scheme works. So let's see one more example. Hope it's not confusing. Uh, yeah. So in this example, we have the number of pages as 2 power 20. Page size is given as 2 KB, and the entry size is 4 byte. So the displacement is 11 and P equal to 20. Now we'll see how we need to split this, how many number of levels we require. Okay, with this detail. So let's again go to find the page table size. So the number of this is pages. To power 20. Okay, so page table, let's find out the page table size equal to number of pages into to power 20 into 2 square, which is 2 power 22. That is 4 MB. Okay. So now this is the page table size. So now let's see how many pages will we need. Number of pages needed for page table will be PT size divided by page size, which is equal to 2 power 22 by page size is 2 power 11, which is 2 power 11. Okay, number of pages needed for the page table. Now let us see how many entries the page can accommodate. Okay. Number of page table entries in a page, which is equal to again page size by page table entry size. Page size is here 2 power 11. Page table entry size is 2 square 4, right? So it is 2 power 9. Right. So each page can have only 2 power 9 entries. Okay. Now, if you see here, number of pages needed for page table is 2 power 11. Okay. So, this 2 power 11 entries also cannot go into a single page. In the previous example, if you see here, the number of pages required was 2 power 6. Number of pages required for the page table was 2 power 6, and each page was able to accommodate 2 power 9 entries. So this was lesser. So we just we could have 2 power 6 entries in one page. That is the outer page. But in this scenario, if you see here, we can have only 2 power 9 entries in a page table. So now number of pages. So if we want to keep all this pages information, we need 2 power 11 entries in a page, which is also not possible. So we need to again split this to 2 power 2 plus 2 power 9. So this, so how the hierarchy will be? So we will have the logical address will have, so we will have 11 bits for the displacement. So we will have 3 levels now. This is P1, which will be 2 bytes. This is P2, which will be 9 bits, and P3, which will be 9 bits. Okay. So this is how the hierarchy is formed. So this page 2 power 11 pages also cannot be accommodated in a single page. So we again need, so this many entries we need, right? So this again we cannot accommodate. So how many pages do we need for this? So this is again 2 power 11 by 2 power 9. Okay, because each page can accommodate 2 power 9 entries. So 2 power 11 by 2 power 9, that is 2 square outer pages we need. Okay, so that is how the hierarchy, the multiple levels are formed. So in this example, we need actually 3 levels of paging. First, outer page will have 2 power 2, that is 4 entries. Then the next level will have that many 4 different pages, and the next will have again that many different pages, and then we'll go to the final frame size. So we at level 1 P1 we will have, then P2, then this can go to this many, so it will be a lot. Okay, then we will have the final paging. So this is how the multi-level paging works. Any doubts? Okay. We'll go to another question. You remember? Another question on this paging is there's a three-level paging scheme. 56-bit logical address space. Page sizes. 4 KB. Inter-page table sizes. Second outer page table sizes. 128 KB. And inner page table sizes. 4 KB. Now each entry, I'll write here. Each entry in the page table four bytes. How many bits are required? Outer page table. Second outer. And inner page table. And offset. Okay. So it's a three-level paging scheme. It's 56-bit logical address wherein the page size is 4 KB. So 4 KB will be 2 power 2 into 2 power 10, which is 2 power 12. Okay. So offset is 12 bits. Now, how many bits are left? 56 minus 12 equal to 44 bits. Now, this 44 bits is split to three portion. That is P1, P2 and P3. This is 54. Okay. So it is given that outer page table size is 2 MB. So how many entries and each for outer page table size is 2 MB and each entry in the page table consists of 4 bytes. So number of entries in the outer page table will be number of entries. Table will be outer PT size divided by PT entry size. Oh no, I just think where did the writing go? Hmm. Let me rewrite the question again. 3-level paging scheme, 56-bit logical address, page size 4 KB, 2 power 11. Outer page size is outer page table size is given as 2 MB. Second outer PT size is 128 KB and inner PT size 4 KB. Each entry in page table is 4 bytes. So the question is how many bits are required for outer, second outer, inner and offset. Inner page table and offset. Okay, so we have 56 bit. So of that 2 power 11 is offset. 7 equal to 11 bits. We have a 3-level paging. So the 56 minus 40, 56 minus sorry, 2 power 12. Minus 12, which is 54. We have P1, P2, and P3. And this is 44. Okay. So number of bits for outer page. Let's see, number of bits is equal to the number of entries. So number of entries in outer page table. Outer PT equal to outer PT size by PT entry size. Outer PT sizes, outer page table sizes 2 into 2 power 20 divided by 4, which is equal to 2 power 90. So number of entries in the outer page table is 2 power 19. So this means 19 bits are needed. Now for the second outer table, entries. Second outer table size 128 KB by 4. 128 KB is 2 power 17 by 2 square, which is equal to 2 power 50, which implies 15 bits. Now let's see the inner page table. So inner page table size is 4 KB by 4, which is 1 KB, which is 2 power 10, which implies 10 bits. So for outer, we need 19 plus 15 plus 10. So it is offset is 12. Inner we needed 10. Then we needed 15. Then we needed 19. Okay. That was one question. Then moving on to the other topics discussed in the class. Basically, yeah, the matrix translation. Then the other paging approach for large page table is hash page table. So in hash page table, we use a hashing mechanism. We give the page number, and then we get the hash will give an output, and based on that, the physical address will be retrieved. But here with the hashing, there is something called collisions that happen. So we may have to scan through the list of all those entries that have hash to that location will be maintained, and there will be a search on the list will also adds in when we are going for hash page table. Another one is the inverted page table. Here page table will have a mapping from the frame to the pages. So the size of the page table is fixed. It will be the number of frames available, and then it tracks like which process is associated or given this particular frame, the process ID, and those details are tracked. So here again, the issue is like in from the inverted page table, one need to do a search on the PID and page number. So that, but here the page table will be very small, but this is the disadvantage in inverted page. The other topic that started was with respect to virtual memory demand paging. So, wherein the concept of demand paging is that bring in the pages to the main memory only when that part of the code, the processor access that part of the code which is there in that particular page. Otherwise, don't bring it to the memory. That is demand paging. So this needs additional hardware support and all to keep track of what are the pages present, what are the pages not present, and swapping mechanism to help move in and move out the pages and all that. See, the other another aspect that was introduced was this concept of valid and invalid, which will help us whether identify the MMU will be able to identify whether the page table entry have a valid address or an invalid address. If this valid invalid bit is set, it implies that it's a valid address, otherwise it will be an invalid address. In the concepts of page fault and page replacement, page fault was discussed. So page fault is a scenario wherein when you're trying to look up for a particular page, it's not available, and then that page has to be loaded from the secondary storage. That is a page fault. So the process will be blocked until it is brought in and all that. So now further upcoming topics will be if page fault occurs, we need to bring in a new page and put it. But what if all the available slots are full? We need to replace some existing pages and bring in the new pages. So what are the algorithms and mechanisms used to do this page replacement and all? This will be discussed, I think, in the upcoming class. So now we can go through the last year's questions. So one of the I'll just the first question as a problem actually. I'll quickly do this with the screen sharing and then we'll know. So in a paging hardware with the TLB, entire page table on odd pages and so it's a question to compute the effective memory access time given that 10 millisecond TLB access time, 80 millisecond memory access time, and the hit ratio of 0.6. So the formula is effective access time equal to hit ratio into TLB access time plus memory access time plus miss ratio into TLB access time plus 2 into memory access time. So here hit ratio is 0.6, so miss ratio equal to 1 minus hit ratio, which is 1 minus 0.6, which is 0.4. So effective memory access time is 0.6 into 10 plus 80 plus 0.4 into 10 plus 2 into 80. So the answer is 122 nanosecond. So I'll share it via the screen. Yeah, so this was the question. So here the answer is 122, that is B. The next question is the ability to execute a partially loaded program enables consumption of less memory. Hello.
फर्स्ट आंसर क्या होगा
Hello.
सर?
The question is the ability to execute partially loaded program enables A, consumption of less memory by each program while running. B, requirement of less IO for loading, swapping programs into memory to run more programs at the same time for better CPU utilization. So all of these are correct in case of partially loaded program. So this is the advantages of demand paging. So the answer here is D, all of the above. So the next question is, sorry. Next question is, which of the following is incorrect about demand paging? In pure demand paging, process starts with more pages in memory. Yes, that is true. So first itself, it will start with the page fault. A given instruction can access multiple pages and page faults. Yes, that is also true. Support for page table, invalid written secondary memory like swap pages are required for demand paging. That is also true. So all of these statements are true. So nothing is incorrect. So here the answer is D. For implementing demand paging, it is required to distinguish between the pages that are in memory and the pages that are on disk. That is true. We need to use a variation of valid invalid scheme for protection. We need to implement new MMU functionality also, memory management and functionality also. So all these three are true. It's needed for implementing demand paging. So here again, the answer is all of the above. Now, next question. Virtual address space does not facilitate the following. System libraries are um, shared via mapping into virtual address space. Process creation is speeded up. Process creation is speeded up by sharing pages during for that is true. Virtual address space does that. We can do the libraries sharing also. That is also facilitated by virtual address. Sparse address space are left with holes for growth. That is also true. So here again, so virtual address space facilitate A, B, and C. So here again, the answer is D, none of the above. The next question is Oracle Spark Solaris uses two hash tables. So just the following is incorrectly specified about that architecture. So each hash table maps memory addresses from virtual to physical memory. That is true. Each entry has base address and span. Having a single hash table is more efficient than the given two hash table architecture. So that is false. Each entry represents a contiguous area of map virtual memory. So the question is incorrectly specified. So the answer here is C. So which of the following is incorrect about virtual memory? It allows address spaces to be shared by several processes. It can be implemented via demand paging or segmentation. Physical address space is larger than logical address space. It let more programs run simultaneously. Incorrect about virtual memory. It allows address space to be shared by several processes. True. It can be implemented via demand paging or segmentation. That is true. Physical address space is larger than logical address space is incorrect. Yeah, so here the answer is C. The virtual address space is larger than physical address space. Next question. When the valid invalid bit is set, is set to valid, it means that associated page is in the TLB, has data in it, is in process logical address space, is in systems physical address space. So when we set the valid bit to 1, it implies that the page it is available in the physical address space. So here the option is D. Find out the incorrect statement. Demand paging brings a page into the memory only when it is needed. Demand paging can bring entire process into memory at load time. Demand paging requires more memory than normal paging, none of the above. So demand paging requires less memory actually because only the needed ones are brought into memory. So C is wrong, incorrect statement. So the answer here is C. So in an inverted page table, there is one entry for each real page of memory. It tracks all pages rather than having a page table for each process. There is one entry for each real page of memory, that is true. It tracks all pages rather than having a page table for each process, true. Consists of virtual address of the page stored in that real memory location with information about the process that owns that page. This is also true. So here again the answer is all of the above. Yeah, so with this, yeah, we are kind of done. So if you have any other queries or doubts, we can do that. There are no doubts, then we can close the session. If you have any queries or any topics, if you want to be discussed, you can put it in the chat or you can unmute and thank you and close the session. Thank you.